Hi everyone. In this video, you will find out the solution for one of the problems in our exam. Indeed, it's a root locus analysis example in which a system given for us provided as the GP that you can see here, which has three poles at -1, -3, and -5. We need to draw the root locus for this system. Then we need to check if there is such a K for which the closure pose of the system will be located at -1 plus -J2. And as the third point, we need to find out for which value of K1 of the closure pose of the system will be located that is equal to -4 and then determine the location for the other pose of the system. So let's start by the first point of drawing the root locus for the system. We have GP given as three poles at -1, -3, and -5. Therefore, we have n equal to 3, m equal to 0 number of zeros of the system. As a result, the difference between n and m, which is equal to 3, and it's the number of asymptotes for the root locus. So we have three asymptotes for which we can find out the point of abscissa, xa, sum of zi minus sum of pi over n minus m. There's no 0 for the system, n minus m is equal to 3, so we will have -1 plus 3 plus 5, which is equal to -3. And we have r times kca given as 2h plus 1 times pi for positive locus and 2h pi for the negative locus. And since r is equal to 3, we will have h equal to 0, 1, and 2. As a result, we will have 3 times kca equal to, setting h equal to 0, 1, and 2, we will get pi, 3 pi, 5 pi for the positive locus, 0, 2 pi, 4 pi for the negative locus. And if we divide everything by 3, we will have kca given as pi over 3 pi, 5 pi over 3 for the positive locus, and 0, 2 pi over 3, and 4 pi over 3 for the negative locus. So we know all the information regarding the asymptotes, and we can already start to draw the root locus. Let's prepare one graph for each, for the positive locus and for negative locus. We can start by determining the location for the poles. We have one pole at -1, one pole at -3, and the pole at -5. And the same thing for the negative locus. To draw the asymptote, we need to find out the point of abscissa, which is -3. It's here. For the positive locus, we have pi over 3 pi and 5 pi over 3. So this is what we have for pi, and pi over 3, which is 60 degrees, could be something like this. And for negative locus, we have 0, 2 pi over 3, and 4 pi over 3. Starting from -3, this is one of the asymptotes. And then 2 pi over 3 and 4 pi over 3, something like this. Yeah? Not the exact drawing, because it's already enough for us, yeah, to draw it in this way. So we have the asymptotes. As the next step, we can determine the segments of the real axis which belong to our root locus. We have different segments for this example, from -infinity till -5, from -5 till -3, -3 till -1, and from -1 till +infinity. We need to determine the number of poles and zeros on the right-hand side of each segment. Here we have 0, 1, 2, and 3, the number of poles on the right-hand side of the region. As a result, we can see that these two belongs to the negative locus, and these two segments belong to the positive locus. And we can already start to determine them on the graph. So for the positive locus, we have this segment and this segment, and for the negative locus, we have this segment and this segment on the real axis. As the next point, we need to find the break-in or break-away points. Away points for our system, and we already can see from the graph that we need to have one breakaway point for the positive locus between -1 and -3, and we need to have a breakaway point between -3 and -5 for the negative locus. So let's see how we can determine that. We know that to find out the break-in or breakaway points, we need to solve m prime d minus t prime n equal to 0 equation. N is equal to 1, therefore m prime is equal to 0. T is given as s plus 1 times s plus 3 times s plus 5, and it can be expanded to s plus 1 times s squared plus 8s plus 15, or it could be written again as s to the power of 3, 8s squared plus 15s plus s squared plus 8s plus 15. And if we rewrite it, d will be equal to s to the power of 3 plus 9s squared plus 23s plus 15. d prime of s would be equal to 3s squared plus 18s plus 23. And since m prime is equal to 0, we need to only check n times d prime equal to 0, and n is equal to 1. As a result, we will have 3s squared plus 18s plus 23 equal to 0. We need to find out the roots of this equation, and you will find out s1 will be equal to minus 1.84 and s2 will be minus 4.15. So these are breakaway points. One of them belongs to the positive locus, one of them belongs to the negative locus. Minus 1.84 is somewhere around here, so it belongs to the positive locus. This is in positive locus, and the other one belongs to the negative locus, minus 4.15. So minus 4.15, which is somewhere around here. So now we can start to draw the root locus for this system. For the positive locus, we will have a branch starting from minus 5 going towards minus infinity using that asymptote. We will have two branches originating from minus 3 and minus 1. They will meet each other here at the breakaway point, and then we will have the branches going towards infinity using the asymptotes. For the negative locus, one branch will start from minus 1, it will go towards plus infinity, and the other two branches will go towards each other. They will meet at the breakaway point, and then they will go towards infinity using the asymptote that we already have drawn. So one more thing here is that we can determine this point. And how to determine it? We have two main approaches. One is to use the Ross-Horowitz criterion to form the Ross table for the characteristics equation, including the gain k, and then find out when do we have the roots on the j omega axis or on the imaginary axis. The other way is to replace s with j omega, and then set the characteristics equation equal to 0, and from there we can find the value for k and for omega. But for now, for this question, that's not that important. It's already enough in terms of the drawing for the root locus of the system. Okay, so we are done with the first part. Let's see what we have in the second part of the question. We need to determine whether there is a value of k in which the poles are located at -1 plus -j2. Looking at the root locus that we have for positive locus and negative locus, we may think that there might be a point in the positive locus which could satisfy the requirements on the root locus drawing, yeah, in terms of the amplitude and phase conditions. But that value of k could belong only to the positive locus, but because with negative locus, there's no way of having the closed loop pose at this point. So we know for sure that if there's such a k, the k will be positive. But how can we determine whether there's a k or not? We need to apply the angle or phase condition at that test point. So this, in general, when you want to determine whether a point belongs to the root locus or not, you just need to apply the angle condition, and if that condition is satisfied, then that point belongs to the root locus. If not, it doesn't. So we have pose at -1, -3, and -5, and our test point is this point. We have the angle condition given as phase of n over d evaluated at s star should be equal to phase of -1 over rho. In our example, it's equal to -1 over k. And since we already know that k is bigger than 0, here we will have minus pi. For n, we have only 1, so phase of n over d will be equal to minus phase of d. And to find out the phase of d, we just need to connect each pole to the test point, draw a line from that pole towards plus infinity, and then determine the value for the angles here, theta 1, theta 2, and theta 3. So the phase of n over d will be equal to 0 minus theta 1 plus theta 2 plus theta 3. And we need to check whether this is equal to minus pi or not. So for theta 1 here we have J2. For theta 1 we obviously have pi over 2. For theta 2 we have pi over 4 because here we have 2 and here we have 2. And for theta 3 we have inverse tangent of, here we have 4 and 2, 2 over 4. Or inverse tangent of 1 over 2, which if you find out the value is equal to 0.46 radian, or it's equal to 26.5 degrees. So the sum of the angles that we have here will be equal to 3 pi over 4 plus 0.60 radian, or it's equal to minus 135 plus 26.5, which is indeed equal to minus 161.5. And it is obviously not equal to minus pi or minus 180. So we conclude that there is no GC of S equal to K for which we have a pole at S1 and 2 minus 1 plus minus J2. Let's see what do we have in the last point. We need to find out the value of K for which one of the poles of the closed loop system is located at S equal to -4, and then determine the location for the other poles of the system. Looking at the root locus plot that we have, we know that S equal to -4 belongs to negative locus because it's here, somewhere between -5 and -3, and we can see that it doesn't belong to the positive locus. So S1 equal to -4 belongs to the negative locus. We need to find out for which value of K we have such a pole for our closed loop system. And to find out that, we can refer to the amplitude condition. So our test point here is at -4. To find out the value of K, we need to apply the amplitude of n over d at S star, which is equal to amplitude of -1 over rho, or in our case, it's equal to amplitude of -1 over k. To find out amplitude of n over d at S star, since n is equal to 1, we will have 1 over amplitude of d at S star could be found by multiplying the distances of the poles from that test point. Here we will have 1, we will have 1, and we will have 3. So 1 times 1 times 3, which is equal to 1 over 3. And this is equal to amplitude of minus 1 over k. As a result, k is equal to plus minus 3. But since k is in the negative locus, we will have k equal to minus 3. Now to find out the other roots of the characteristics equation or the closed loop pose of the system, we need to form 1 plus k times n over d equal to 0, replacing k with minus 3. Therefore, we will have d minus 3 equal to 0. We have the expression for d already. Yeah, it's here. So d minus 3 will result in s to the power of 3 plus 9 s squared plus 23s plus 15 minus 3 or plus 12 equal to 0. And we already know that there is a root at minus 4, and then there are two real roots, because one of the roots will be somewhere around here on the right hand side of minus 1, and one of the poles will be between minus 3 and minus 5. So therefore here we will have s plus a times s plus b equal to 0. And from here you can find out the value for a and b, where a would be equal to minus indeed 0.69 and b would be equal to 4.30. So we will have s1 at so here we have s plus 4, s1 at minus 4, s2 at minus 0.69, and s3 at minus 4.30. And we are done with the question. Okay, so that's all for this video. Thank you for watching, and let me know if you have any kind of question or feedback regarding this video or any other videos that I have on my YouTube channel. Thank you for watching, and see you next time.